Welcome to the project presentation of Power System Protection. I have chosen the topic Design a low-cost wind energy system for a Canadian single family to reduce their electric bill. I would like to thank Professor Dr. Mohsin Jamil for his valuable support and guidance. Our main objective for this project is to design a small-scale renewable power generator which can be implemented in a remote location. We would like to try on-grid off-grid combination which will help to reduce our electricity bill in one way and also provide us backup power supply in another way if our microgrid fails. This will help to reduce carbon emission and cover most of the day-to-day light power consumption of a Canadian family.
Why we have chosen wind energy system? We all know St. John's is the second windiest province in Canada. It is one of the windiest city in the world as well. It's also true that wind energy is carbon free and there is no fuel cost included with this type of energy generation. And we also know that it includes low operating cost and it reduces grid dependency as well. Being a windiest province, as we all know, wind flows almost in same speed all over the year in St. John's. So we can expect longer sustainability from this type of energy generation system. As we are also planning to place this system in a remote location so we can get good source of energy from this type of resources, and this project is also convenient for remote location. At first, we need to select the site for our project. We all know this plays a crucial role in the financial return of the project. If we select an inappropriate site, we might jeopardize the benefit of the project. We have chosen a remote location situated in the Signal Hill Road, which is in the southeast part of St. John's, and that's a coastal region. There is a benefit for choosing this site. Coastal wind projects can contribute to increase the installation capacity and they ensure frequent and powerful winds. We all know, as a remote location, there is no nearby obstacle that will cause turbulence and the disruption in the airflow, and that will be beneficial for our power generation. The height of the tower will be comparatively less as the site is located in higher elevation and there is no obstacle. So we can get fluent wind flow and that will be helpful for our project as well. Here is a bar chart where we can find the average wind speed of our desired location for different months of a year. We can see the annual average wind speed of our location is 7.78 meter per second, which is ideal for setting up a small scale wind turbine system. We can also see that this wind speed increases in January, February, and in the month of November and December, where our energy consumption increases for the winter season. So, this wind generation system can generate more energy at that time, and that will be helpful to meet up our excess demand. Here's the research methodology of our project. At the right side, we can see an algorithm which depicts the pathway for optimizing our whole system. We have done basic optimization using Homer Pro optimization tool. We have used MATLAB Simulink for dynamic simulation and observed the system output at varying site condition. We have also introduced a PID controller to demonstrate the system control and the protection of the whole system. As we have previously told, our main focus is to reduce the electricity bill, and we have targeted at least 70%. And we have also targeted to reduce the capital and operation and maintenance cost with maximum utilization of our available resources. At first, we need to find out the total consumption of our desired remote house. At the right side, we can see different kind of appliances which we use in our daily life. We have calculated the consumption of different appliances at that house, and we have tried to find out the total load of that house. We have followed this formula to estimate the load, where we can find the total wattage hour is equals to number of electrical appliances multiplied by their operational hour and the total wattage of these appliances. After that, we need to select the wind turbine for our project. For this operation, at first we need to calculate the total power. For this, we are considering air density, the blade shift area of the wind turbine, the blade radius, and the wind speed of that area. And we are following this equation to calculate the wind power. After the calculation of the available power, we will solve the actual power output of the turbine by following this equation. We also need to calculate the actual output power by considering the factors which are tower height, side shear factor, and Weibull probability distribution that will help us to select the proper wind turbine for our project. We are considering batteries for our project. Though our system is grid connected, there may be some natural disaster or some malfunction from the wind turbine or at the grid. To continue seamless power delivery, we are considering batteries with the system. To sizing the batteries, we have to calculate the total battery bank capacity. For this reason, we are multiplying the total wattage hour and the number of the days for which we are considering the backup. We are considering the depth of discharge as well as the temperature effect for our batteries too. After that, we are calculating the total ampere hour of the battery. For this, we have to divide the total battery bank capacity with the rated voltage of the selected batteries. And then we have to count the total number of the batteries we are selecting. By following these equations, now we have to calculate the battery for our project in different steps. At first, we have considered the daily consumption of our remote house is 16.35 kilowatt as we are taking the backup for a day. So considering the depth of discharge for the lithium ion batteries 80%, we can find the total kilowatt is 20.43. Then we are considering the temperature effect. At the right side, there is a chart where we can find the temperature factor for the lithium ion batteries. At 25 degrees Celsius, the temperature factor is 1.01. So the capacity of the battery system will be 20.64 kilowatt hour. Then we have to calculate the ampere hour of the battery system. As our system is of 24 volt, so we have to divide the result of the step volt, that is 20.64 kilowatt, with total volt, and we can find the ampere hour for system, that is 860 ampere. In step 6, we need to identify the number of the batteries which we need to back up our system. If we consider a 110 ampere lithium ion battery for our system, and as our total consumption is 860 ampere hour and our system is of 24 volt, so we need 8 batteries to back up our whole system. Considering the load demand of the residents and the approximate emergency days, we have chosen the battery named Enersys Power Save. The nominal capacity of this battery is 6.46 kilowatt hour. As this battery is of 12 volt, so we have connected two 12 volt batteries in series to meet up with 24 volt system.
Let's have a look at our required components. Following the previously described method, we have chosen LO's 1 kilowatt vertical axis wind turbine because this type of wind turbine provides better output considering our location. Its rated capacity is 1 kilowatt, and to generate that power, we have to maintain the tower height of 9.9 meter and the wind speed of 10.3 meter per second. We need a DC to AC inverter of 24 volt, which we have considered as per peak load. We also need a charge controller and two batteries of 12 volt with the power of 6.46 kilowatt hour. We have used Homer Pro and PSCAD for optimization and simulation, respectively. For optimizing the system, at first we have downloaded the wind resource data of our specific location and inserted per our load consumption of our selected house. From the bar chart, we can see the variable load demand at different time of the day. Then we have selected the components to meet up the load demand. We did the steady-state analysis in Homer Pro where we used fixed wind speed and pitch angle. And for the dynamic simulation, we considered variable data in PSCAD. This is the schematic diagram of our system from Homer Pro. The selected house has the daily consumption of 16.35 kilowatt hour with the peak load of 3.37 kilowatt hour. From the diagram, we can see the system has one AC bus and one DC bus. The grid and the wind turbine is connected to the AC bus and the battery with DC bus. And the inverter is connected with both AC and DC bus, which also acts as a bus coupler. Let's talk about dynamic simulation. In steady-state analysis, we considered fixed input for pitch angle and wind speed, but the actual output depends on the variable inputs according to the site condition. These variable parameters will change the average output of our proposed system. So in PSCAD, we have used variable wind speed and pitch angles. On the right side, we can see the output power curve from the system in variable wind speed. After changing different combination of variable values, we were able to get the output of 1 kilowatt from the wind turbine. We got the value at the wind speed of 7.78 meter per second and the pitch angle of 0.75 degree. We have designed a simple PID controller in MATLAB Simulink to demonstrate how it reacts when the input parameters exceed its rated value. Depending upon the requirements, the PID controller monitors the analog parameters from the input terminals. If the parameters exceed its rated value, the output activates the signal to the turbine to operate in a desired range. As per the manufacturer's rating, the voltage source has been given in line with neutral terminals. The number of input and output contacts depend on the specific protection requirements of the customer. As per the diagram, a closed-loop PID controller has been designed in Simulink. The summation block senses both input and output signals. This block continuously monitors the output parameters with its reference value. As per the settings, when the parameters deviate from their original rating, the proportional, integral, and derivative blocks rectify the input values accordingly and provide output signal so the turbine can operate in its safe range. This is the PID controller simulation graph. Here the red line represents the rated voltage and the blue line represents the actual voltage. When the generation starts, the actual voltage starts to rise from zero and after a certain time it crosses the rated voltage. Then it starts falling down and stables at rated voltage. That means the controller reduces the actual voltage by controlling the input variables. The controller repeats the same process during the whole time of generation to maintain the desired output. Here is the optimization result from Homer Pro. As our project lifetime is 20 years, the optimization shows the NPC is $21,907. That includes the turbine, battery, and the inverter installation cost. Besides, the operation and the maintenance cost and the replacement expenses have also been considered. The levelized cost of energy is 0.49, which is the average generation cost of the wind turbine system in its lifetime, and the renewable fraction is 77%. That means the 77% of the required energy can be generated by the renewable energy sources. This is our final result. From the table, we can find the consumption of our selected house is 5,967.75 kilowatt yearly, and our microgrid generates 4,634 kilowatt per year. As a result, we need to purchase the rest of the required power from the grid. So, to utilize the hybrid scheme, we have to use a net metering system because we have to use the electricity in bidirectional way. This whole process will reduce a significant portion of electricity bills, which is around 77%. We also conducted a feasibility analysis of our project. To generate this cash flow diagram, we have considered the installation and maintenance cost of wind turbine and battery storage system and per unit electricity charge from Enel Hydro. Currently, per unit electricity charge is 12.38 cents. The customer charge we got is $15.81 per month. So the cash flow diagram shows the project will reach to its equilibrium stage after 14 years if they continue saving the electricity bills as per the current situation. For the next 6 years, the customer will get profit from this project. This analysis is based on steady state because the electricity bill may vary per month and the microgrid may need more or less operational and maintenance cost based on the condition. So the cash flow diagram actually depends on various conditions of the site. That's all for today. Thank you so much for your valuable time and patience.